Okay, so we managed to go through an example of finding the loop invariant and then formally proving the Hall triple that we were given using our new while rule. Now, that's all well and good, but the problem is that what we've proven doesn't guarantee that this code actually terminates for all inputs. There could be some silly input where the code just runs forever in a loop. So what we're trying to prove now is we're trying to prove a stronger property. We're trying to prove all the things we did before. So we're trying to prove that for a given input this Hall triple is valid, but we're also trying to prove that the code is guaranteed to terminate. So now we use a stronger rule. We use the total correctness while loop rule, which requires finding another thing. So P was the invariant, and it was a thing that satisfied the three properties listed here. There we go, as we talked about before. Now there's another predicate we have to find. We have to find E, and E is called the variant. And we have to prove a stronger property now. We have to prove that if P and B and E is equal to N, and then I run the code, P still holds, so P is still an invariant, and E gets strictly smaller. So E is called a variant because in this case it changes as you do the loop. But importantly, every time you call the function, E's got to progress closer and closer and closer to 0. And it's also going to be the fact that when you initially run the code, i.e. when P and B are true, that implies E is greater than or equal to 0. So first off, how do we find the variant? That's the first thing we should worry about. So we do the same sort of trick as last time. I've got my little table of numbers, so let's bring him back. Here, I need to try and identify a variable or some collection of variables that's like strictly getting closer and closer to 0. And this is the wrong piece of paper, I'm sorry. Where are we? Here we are. There we are. That's better. Sorry about that. So I was getting bigger and bigger. T was getting bigger and bigger. We want to identify something that gets strictly smaller each function call. Well, neither I nor T will work, but hopefully I can build something out of the variables I'm given. Well, if I gets bigger and bigger and bigger, N take I is going to get smaller and smaller and smaller, right? And when N take I is 0, that's when this condition gets violated. So it seems like a good guess for E is probably going to be N subtract I. And when you're trying to find the variant, a good trick is to find the thing that's increasing and just find an upper bound for it and subtract that. So you want your variant to be, generally speaking, greater than or equal to 0, so that way you can prove this property here. So it looks like N take I is probably going to work. So let's have a look at that. If I choose E is equal to N take I, also I fibbed a bit here. This N here has to be a completely new fresh N, so like where N does not appear elsewhere. Appear elsewhere. So N is like a fresh variable. So if we're already using N in my code here, I can't really use N in the correctness rule. I'm going to have to use like some other letter. I'll use M because I'm very uncreative and M is the letter next to N. Okay? Where was I? Okay, so we have two properties you have to prove. We have to prove P and B implies E is greater than or equal to 0. And I have to prove this whole total correctness Hall triple here. So we'll worry about just this one for the moment. So what was P? P was T was equal to I factorial. And what was B? B was I strictly less than N. If these two properties hold, is it the case that N take I is greater than or equal to 0? Well, what's an equivalent way of stating this? An equivalent way of stating this is N is greater than or equal to I. Another way of saying that is I is less than or equal to N. So it certainly looks like if I is strictly less than N, then I is less than or equal to N. So this is definitely true by logic. And then we have to prove this statement here. This is going to be another statement we have to prove via Hall logic. So assuming we've done that, we can apply the total correctness rule to get us down to here. And then from here, how can we get to the actual thing that we want? It's actually exactly the same as before. So once we get to this statement here, but with square brackets instead of squiggle brackets, we can just do the same steps we did before to get down to the thing we actually want, but this time with total correctness rather than partial correctness. So we'll do this part of the proof. We'll apply the while total correctness rule, and then I can just stitch this part in the bottom. Okay? So we'll do that in the next video.